Hello student, I'd like to take the time with you to go through the first chapter on regular languages and see what are the important results or points in this chapter and, and just to give you a little overview and maybe focus on a few things. So, you've probably read already all of it and studied it. It's important to remember the definition of a finite automaton, which is going to be, five tuple. So you have Q, the set of states, right? Sigma, the alphabet, the set of atomic symbols that can be accepted as inputs. You have the transition function delta, the start state, the initial state Q0, and the set of final states or accept states F. And so first we looked at what we called DFA, deterministic finite automata, and then we look at NFA, the non-deterministic finite automata. The deterministic finite automata are a bit more simple in some sense because simple at first to grasp because they will only accept a deterministic finite automata will only accept one option, one transition for same input and the same state, right? So if you have input 0, you go from Q0 to Q1, for instance. While a non-deterministic will accept, for instance, 0 to loop back to Q0 or to go to Q1. Okay, so that's non-deterministic. You have these two options. With a non-deterministic, you also have the possibility to accept an empty string, right? So basically, without any additional input, it can either stay at Q0 or go to Q1. Okay, so that's the difference between deterministic and non-deterministic. So basically, non-deterministic is a generalization, right? It's a generalization. So here you have a generalization here. What does that mean? Well, that means that if it's a generalization, basically that means that a DFA is an NFA, right? So that's the set of DFAs, and that's the set of NFAs, right? Sorry. So a DFA is an NFA, right? It's also, it has, that's why we can say that one is, the NFA is a generalization over the DFA. Why? Because we relax some constraints, okay? So they're both gonna have the same definition. The difference is that instead of the transition function, instead of here having delta of Q0, 0 equals Q1, okay, for DFA, an NFA will have a definition such that you can have a set Q0 and Q1. It's actually always a set, right? Even if you have just a singleton, just one element is always going to go into a set. So the definition is broadly the same, but the transition, I mean, it is the same, but the transition function is slightly different because here for an NFA, you go from Q cross sigma to the power set of Q. Instead of here, you go from Q cross sigma to Q. Okay. So anyway, so that's DFA, NFA. what is interesting, and that's a very interesting result we have here in the book. It's in page 54. Is that NFAs and DFA are equivalent with respect to the language they recognize. So why do we study automata? We study them because they are interesting machine, if we can say, or computations computers in some sense, that recognize a certain type of languages. Okay, so there is, and that's something very interesting in throughout this course, is that we're going to realize that there is a very strong tie between automata and the families of automata and the families of languages, right? So we say that a language that is recognized by such automaton is necessarily a regular language. That's how we call them, right? So we said that these recognize regular languages. So if you take a certain automaton M, then we call let's say it's an NFA. M, we say that M recognizes a certain language, right? We call L of it, okay? So how do we know what it recognizes? Well, here, for instance, in this case, it recognizes only the string 0, right? In this case, it recognizes any string composed of zeros, okay? How do we know that? Well, we have the starting state, and then the automaton can accept a sequence of inputs from its alphabets, sigma. And as long as we end up on accept states, we can say that the string is recognized by this automaton, and the set of strings that can be recognized by an automaton constitutes the language that is recognized by an automaton. And the set of languages that are recognized by finite automata are called regular languages. Okay, and so what is interesting is that whatever you pick, DFA or NFA, you will always have an automaton that the NFA and DFA both recognize as a whole the same family of languages, regular languages, and so we can see this result by finding out that, to prove that this is true, we need to prove that there is absolutely no here automaton that doesn't have an equivalent here, right? That can recognize exactly the same language, right? So if you prove, so that's a proof to show that they are equivalent, is that you can prove that for any NFA there is at least one equivalent DFA that recognizes exactly the same language. Okay, the proof is very interesting, and I suggest you look at it on page 55. I'm not going to go through it right now, but I'm going to try to give you a little bit the gist of it. So equivalence, NFA, and DFA. Well, for that you need to show that any language recognized by the DFA is also recognized by an NFA. That's the first side, the first part, and that's very straightforward, because we just said that all DFAs are NFAs. So of course, a language that is recognized by a DFA is also recognized by an FA, that is to say itself, because it's also an NFA. What is not as obvious is to show that if you have an NFA, you have a corresponding DFA, at least one, that recognizes exactly the same language. So this one is straightforward. This one is a bit more complicated. But here is the gist of it. If you consider so let's look through an example. Let's say 0, 1, 1, 0. Okay. So here we clearly have an NFA, and because from 0 you can go to 2 different places with the input 1. Okay. And we want to show that there is a corresponding DFA that will recognize the existing language. Let's put this one as a accept state. We can build, there is a process to build systematically a DFA, and that's part of the proof, that will recognize exactly the same language. The way you do that is by building many more states, and that will work that way. We're going to build the set of states as the new Q. Okay, so you're going to have Q0, Q1, Q2, Q0, Q1, Q0, Q2, Q1, Q2. Okay, and you actually have also Q0, Q1, Q2. And actually you don't need all of this, but you can, what we can do is go through each of those methodically so that we don't actually use all of them. But you can do the same process for all of them. The transition function from one to the other is going to be fairly simple. You're going to try to consider the union of all the transitions that come from all the states in your set here. Okay, so if I take Q0 and I look from Q0 with 0, where can I go? I can go only to Q1. Okay, so you're gonna have here 0. From Q0 with 1, I can go to Q1 and Q2. Okay, so Q0 with 1, I can go to Q1 and Q2. From Q1 with 0, I can go to Q2 only, right? From Q0, Q1, so you start to see how this works, right? From Q1, sorry, with 0, I can go to Q2, and with 1, I can go nowhere. From Q0, Q1, and actually you could add to this the empty state, and when you say I go nowhere, you go to the empty state. It's kind of useless because we can get rid of this one in the end anyway. From Q0, Q1, so how does this work? You're going to take just the union of everything that is potential next state with your input. So Q0, Q1, if I take 0, so Q0, Q1, and I do the union of all the zeros from Q0 and Q1, I can end up either at Q1, right? And from Q1 I Q2. So Q0, Q1 with 0 go to Q1, Q2. Okay? Like this. And then Q0, Q2, Q0, Q1 with 1, Q0, Q1 with 1 also go to Q1 and Q2, right? So 1 or 0. And now from Q0, Q2 with 0, you go only to Q1. And with 1, Q0, Q2 with 1, you go to Q1 or Q2, right? So, okay. And now we're almost there, right? And now Q1, Q2, if I take the union with the input 0, Q1, Q2 with input 0, I will get only to Q2. And with input 1, I will get nowhere. Finally, the last one, usually this one is not really used, but Q0, Q1, Q2 with 0 will go to Q1, Q2. And with 1, we'll go to Q1, Q2 as well. Okay, now if I try to unfold this a little bit, right, because it's kind of messy, what do we have? We have one here. I'm gonna write it differently so it's less messy, okay, without the brackets. Q0, let me try to, so we have Q0 with 1 to Q1, Q2, and 0, Q1, and 0 to Q2, and Q1, Q2 to Q2, 0. And now Q0, Q1 to Q1, Q2, with 0 or 1. And Q0, Q2 goes to Q1 or Q1, Q2. Goes either Q0, Q2, either to Q1 with 0 or Q1, Q2 with 1. Okay. And we have Q0, Q1, Q2 with 0, 1. And I think we have everything. Okay. So that's a bit better. Now, how do I know the accept state and starting state? Okay. Well, the starting state here, I forgot to mention it, was Q0. It's a little bit more tricky when you have an epsilon. You can look in the book, but right now we're going to assume we don't have one. So it's going to be Q0. It's as simple as that. And the accept state, however, has to be the set of states, all of the states that have Q2 in them, in our case, right? So it's going to be this one, or this one, or this one, or this one. But this one, there's no way to get there from the start state. So it's kind of useless. We can get rid of this one. It's the same about this one. There's no way to get there. So, and if you think about it, it's the same also of Q0, Q2, right? You cannot get there. You can only go from there. So we end up with something actually fairly simple, but Q0, 1, Q1, Q2, 0, Q0, Q1, Q2, Q1, Q2 goes with 0 to Q2, accept state, and actually, yes, and Q0, 0 to Q1, and with 0 to Q2. Okay, so we end up with something actually fairly simple, and you can try it if we've not been mistaken. This will accept exactly the same strings as this, except that in this case we have a DFA and not an NFA. So really the little trick is really this idea of power sets, and if you look at it, the way it works is that what we're saying is that every time we go, if I go from Q0 and I take 1, I go to Q1, Q2. And what does it mean? That means that I remember that from Q0, I can either go to Q1 or to Q2. And I remember that, okay? So my DFA is a bit bigger, it has more states, so that I can remember where I am and when I split, okay? So that's the gist of it, okay? So I think it's an important result. If you can look at it, that's a good thing. Then we have regular expressions. So regular expressions, to really get them, it's really mostly a question of exercises. So I really invite you to do a lot of exercises about them. But regular expressions, basically we show that the regular expressions generate regular languages. So, so the same way we say that a machine recognize regular language, we say that a regular expression, an expression generate a regular language. Okay, so it's not exactly the same verb because this is, a regular expression is not an automaton. Okay, so it doesn't recognize a language. It doesn't recognize and it generates. But they are equivalent. That means that they actually, what a regular expression generates is what a finite automaton recognizes. Okay, the regular expressions, there are some rules. You can look at them, the formal definition in the book, but they will always look like, AB is a regular expression for the alphabet. If we consider the alphabet A and B, you can have AB. A star is going to be a regular expression. That means that you can use anything from, so A star contains the ANSI string, okay, A, okay, etc. Right? You can have as many A as you want. But then you can also define, A star, B star, any number of A from 0 to infinity. I mean, there's no limit. And then any number of B, okay? Star doesn't specify the number. Sigma star is basically equal to A union B star, okay? So there is an exercise at some point in the book about describing a correct comment in a programming language where commenting would be slash, it's actually slash, it's not backslash. But anyway, let's say backslash pond, and then some language, A union, I mean, let's say that the alphabet is still, I mean, you can only write A or B. And then again, so that's a regular expression, right? Pound slash. So that's a regular expression that describes a comment for any string that contains A or B. Okay. And for this regular expression, you can associate, of course, because it's a regular expression, DFA or NNFA, right? In this case, the automaton could be like this one, okay? Backslash Q1, and then pound Q2, and then any A or B, and then pound again Q3, and backslash again Q4. And so you have the description, the same description of the regular expression described as here a DFA. Okay. So that's a short rundown on regular expressions. I suggest you do a lot of exercise with these ones. And on the next video, we will look at the definition of non-regular languages. So what is interesting in this course is to reach limits. Okay, so we have here a whole world of NFA, DFA, and regular expressions, right? These are in some sense are recognizers or generators, and they generate a whole world, right? And this is the world of regular languages. Now, what is interesting when we generate this whole world is to reach its limits and find out what are its limits and what is in and out. And the limit is always a very interesting place to study because it tells us a lot about the in, but it also tells us a lot about what is outside. And what is outside are non-regular languages, and this is what we will study in chapter 2. But before that, the next video, I'll talk about the pumping lemma and non-regular languages. Thank you.